Okay, so you have an electric motor rotating on a wheel at a rate of 80 revolutions per minute.
A what?
It's rotating at this rate. It's a wheel spinning at this rate. And all of a sudden it's switched off. Okay?
Is it T is equal to 2 pi r?
No. What's that? What's T equals to 2 pi r?
1 revolution, which is 360 degrees.
Yeah.
2 pi r.
Oh yeah, that's 2 pi r is just the circumference of a circle. Right?
So
Is that
what's 1 revolution like?
1 revolution is equal to 2 pi radians,
Oh. Okay.
which is also equal to 360 degrees. Right? 2 pi is a full circle. So 1 revolution is 360 degrees or 2 pi. Or, you can think of it like this. If you have a circle of radius 1, the revolution, the distance that it travels, is 2 pi times 1, or just 2 pi. Because it's 2 pi r is 1. In terms of the angle covered, it's the same. Now, it says that the motor is switched off, and then, assuming a constant negative acceleration of 2 radians per second squared, so 2 radians per second squared. So because you turn off the engine, this wheel is starting to slow down, right? And it's slowing down at a rate of 2 radians per second squared.
Is it negative?
Yeah, it's negative, sure. Because it's slowing down. How long will it take for the grinding wheel to stop in seconds? So how much time find t? This is a very easy question. What is this? I want you to tell me in linear terms what would be the equivalent to this question. Someone say that? What? If we had a car moving, what would be the equivalent question that would have been asked?
Don't you
When
want
would
to
we stop?
seconds?
Like when would we stop? At what time would we stop?
Yeah, like if there was a car, what would be the question that would have been asked where it would be the same thing as this but for a car that was just moving in a straight line? Not as the wheel spinning, huh?
The distance?
Yeah, the distance. Well no, the thing is, okay, look. The wheel is rotating at a certain rate. That would be the velocity of the car initially. The guy starts braking, so he's applying a negative acceleration, and he's going to stop after a certain amount of time. How much time does it take for him to stop? That's all it is.
You have to put minutes to seconds?
Where this? Yes, of course.
Yeah.
So I keep putting the chalk back over here. So how do you convert 80 revolutions per minute to angular velocity? Because that's revolution per minute. It's not directly angular velocity. So you just go like this.
Acceleration is equal to b squared over r?
What? B squared over r?
Yeah, no, it's not.
If you do that, that would just give you the centrifugal. If you're saying AC is B squared over r. That just tells you the centrifugal acceleration that's inwards in the circle.
Oh, yeah.
But it's different from the one that's this way. This is the tangential acceleration, which is what's causing the wheel to slow down or speed up. So like 80, if you want to convert 80 revolutions per minute, you go like this, 80 revolutions per, and remember this, because this is, will apply to any other conversions you have to do. You just write it out like that, and you put the thing like this, and you say, I want my final answer to be in radians per second. So if I want revolutions and radians on top, I'll put revolution on the bottom. There's in 1 revolution, I said there's 2 pi radians. Because 1 revolution is 360 degrees. So if I wanted degrees here per second, I would have put this as 360 degrees in 1 revolution. Because I wanted in radians, I put it as 2 pi radians in 1 revolution. Minutes, I want seconds in the bottom. So I put seconds in the bottom, minutes on top. There's, in 1 minute, there are 60 seconds. So I do 80 times 2 pi divided by 60, and I have my conversion.
4,800. Does that make sense? I
4,000.
times it by 360, right? That's okay?
What?
It's 80 times 360.
No, 80 times 2 pi.
Do I actually put pi?
Yeah.
Put pi 180.
No, use pi as the actual value of pi.
That's not radians.
Do I put my calculator in radian? And
No, that only I'm so confused about that. You only have to put your calculator in radians when you're doing the stuff with simple harmonic motion and you're plugging pi into a sine or a cosine or a tangent or something. The rate what?
This is the frequency or
The angular velocity, yes.
so is it the same, the frequency and the angular?
No. The angular velocity omega, which is what we're getting from this, is related to the frequency by 2 pi f.
So this is the frequency?
No, this is the angular velocity. Whatever I get from here, okay, what did you get?
8.38.
Okay, so
That logical? Yeah.
give me a second. 8.38 radians per second. You see this? Look. What I got now is in radians per second, which is similar to when we have velocity. Velocity is in meters per second. So instead of having distance, I have angle per second. Radians is an angle, right? So this, if I have angle per second, that's an angular velocity, omega. If I want to find out how much that is as a frequency, I have to divide this by 2 pi. Because pi is in radians, dividing this by 2 pi will give me something that's some number per second. Number per second is hertz. Because hertz is second inverse. So it's when you divide it by 2 pi that you get the frequency out of the angular velocity. So if you have angular velocity, which is what we just converted 80 into 8.38 radians per second, that was our omega. If I want to solve for the frequency, I have to divide the omega by 2 pi. And obviously once you have the frequency, the period t is equal to 1 over the frequency. In case you don't remember, I'll explain it again. If I move from here to here, I cover an angle of 90 degrees, which is equal to pi over 2. That would be my delta theta. If I do that in a certain amount of time t, my angular velocity becomes my change in position, delta theta over my time. Just like velocity is distance over time, angular velocity is change in angle over time.
It's so confusing when you change around all the letters.
I know, but just think of this as delta x and this as delta v. So delta v is delta x over t, or delta omega, is delta theta over t.
Okay.
The faster I cover the angle, the greater my angular velocity must have been.
So it's faster to cover the same angle if you're close to the center.
What?
It's faster to how do you call it? To cover the same angle if you're close to the center of the circle.
Yeah, you have to cover less distance
Less distance there.
than
But
here.
it's the same.
But the angular velocity will be the same. You're covering the same angle, yes.
But it's faster if you're close to the center.
Yes, you're moving faster.
Okay.
Sorry, you're actually moving faster on the outside than on the inside. You have to cover more distance here. So you have to cover the same amount of time. You have to move faster to cover it there as if you're doing it here. The angular velocity of both people will be the same because they'll cover the same amount of angle in the same amount of time. But this guy will have to move at a faster linear velocity to cover all his distance, and this guy wants to cover less distance. And you can see that if you say omega is v is r omega. So the linear velocity for any given angular velocity, the linear velocity is the angular velocity times the radius. So this guy has a smaller radius than this guy, has a bigger radius. The linear velocity of this guy will be greater because he's moving the same angular velocity at a larger radius. Now, if omega is delta theta over t, then at alpha, the angular acceleration is delta omega over t. The change in velocity over time gives you the angular acceleration. From this, if you put t over here and expand this, you get that omega final is equal to omega initial plus alpha t. Do you see that? This is final minus initial. T and A is here, final and initial. So we have an equation that we can get directly out of here from this from here. And so for this question here, what we have is we have an initial angular velocity, then we have an angular acceleration, and we know that it goes down to 0 at the end because it stops completely. So using this equation, I can just say if my omega final is 0, my initial one was 8.4 plus the angular acceleration, which was minus 2 times some time. I want to know how much time it takes for it to slow down, so I can just solve for t right here.
Where did you get 8.4?
That's
Oh, that's the number we solved for before.
we converted here for angular velocity. So 8 minus 8.4 divided by 2 is, what is that, 4.2?
Yeah.
So the time is 4.2 seconds. See, this question would have actually been very easy if I didn't do what I was talking. I'll just take this, multiply it by 2 pi divided by 60, take that value, plug it in here, and then solve for t. It would take literally like 30 seconds.
Well, what's that minus 2 thing? I don't get it.
Because the wheel has as it's slowing down, it has a negative angular deceleration of 2 radians per second.
Okay.
So that's why I put minus 2 in there.
So it looks like mx plus b.
What?
It's like a
Yeah, mx is like a linear equation, but really all I did is I used this equation, which is the same as v final is equal to v initial plus at, one of the first kinematics equations. I'm only just using that equation with omega for v and alpha for t. Okay, I'm going to do another question.
You should do
Or what?
energy.
You're stuck on energy? You're stuck on angular stuff and torque?
No, you know what? This angular, like rotational motion, but not the easy one. Because sometimes they ask us just centripetal acceleration and stuff like that. That's easy. But when we start mixing up with tangential acceleration, radial acceleration, and like those all components, and also non-uniform circular motion, that's also I'm stuck in that a little bit. And energy. Well, no, I think I cleared a little bit of energy today. But yes, like acceleration, even more complicated.
Yeah, but this is actually a very easy question. It's cool that I managed to explain it, but you guys, you missed one of the classes. I did like a question that took like almost the whole class. It covered everything. Yeah.
Yeah, the one with the he goes down and he goes up with the frictions and the angles there.
Yeah, and there was a wheel spinning,
Loopholes, yeah.
and you have to find like it's too bad you missed that one because that was really good.
What about oscillatory motion? Is that kind of like circular motions, or is that like?
No. The oscillatory stuff is like simple harmonic motion. You mean, right?
Yeah.
Like a pendulum swinging, or a box moving back and forth in the spring. Those are standard simple harmonic motion. You know what I mean?
Yes, because we didn't really go over it. So it's like.
Okay, well, if you did. Alright. If you haven't covered that. Okay, what's the angular velocity in a situation where you have a pendulum, certain mass, and the length swinging?
Like a clock thingy, or like a thing where it pops up the other side?
No, it's just swinging like a clock, yeah.
Okay.
What's the angular velocity in that case? Square root of L, G over L or L over G.
Oh, that. L over G?
Yeah, if you think about these things, and you realize that independent of the mass, the period of the pendulum will be fixed by the length and the gravitational force. What about the angular velocity of a spring attached to a box? So you have a wall, a spring, and a box. You pull it and let go, the box will start doing this.
Oh, like in Super Mario.
Mm-hmm.
You get stuck. No? The mushrooms are hitting you? Okay.
Mushrooms hitting you?
No, you jump, yeah, the thing looks like a mushroom, and then they get stuck and they're like, Super Mario, guys.
Oh,
like the ghetto cartridge.
You're talking about the...
It's like
Like
little
mushrooms
mushrooms,
slide off
and
the
they kill
ground and
you.
they bounce off the walls and they
Yeah, just like
It's
this.
just quick.
Yeah, it's kind of like that, yeah. It's just mushrooms, those are turtles.
Turtle! I thought it was a mushroom.
They're actually turtles, yeah.
Yeah.
Turtles.
Yeah.
Well, the mushrooms can actually go back and forth too if they fall into an area where they usually mate so they fall into a ditch. So to catch it. You know? I actually just played a whole bunch of Super Mario on the Wii the other day. It's really good.
Oh, where you can play multiple people?
Yeah, like if you play 4 people at the same time, it's pretty wild. And you can like take each other and throw each other and like jump on top of each other and like, go higher. It's very good. I should go back place more. Yeah, so the angular velocity in a spring system like that. Why do I keep moving the damn chalk? It's weird.
Is that K?
K and M. So what that means is if you have a box of mass M, spring constant K, the angular velocity of the system will be square root of K over M. So as you can see, it doesn't matter if you stretch a spring up to here or only up to here. Independent of that, the angular velocity, which is related to the frequency of the motion and therefore to the period, will be set entirely by the spring constant and the mass in the system. So it doesn't really matter if you stretch it more or less, or if you push it. It doesn't really, either way, the angular velocity will be set. So do you guys know how to use these equations? I actually forgot we were recording this, so we were just talking about like wire. It's pretty funny. I actually did at home in the previous lecture. I talked about this. Yeah? Rings a bell, right? What's the next equation after this?
P,
Yes?
which is V,
Instead
A.
of reading it, do it from here.
Oh, I remember that. You have to, well, what I did in order to demonstrate that was taking derivatives.
Exactly.
So that's
They're all derivatives of each other.
minus W. I have a question. I don't know why, like in my class, the teacher once said to consider like the inside angle as 0. So I don't know if I should leave that equation with A equals WT, just like that, or with the angle.
This?
Mm-hmm.
Okay, this is the phase angle.
Mm-hmm.
Okay?
So,
The initial phase angle.
mm-hmm. So why did he say to take it as 0?
Because sometimes, okay, now, okay, if I draw this,
Are you taking derivatives?
what? Am I doing what?
Are you taking derivatives?
Yeah, this is the derivative of that, this is the derivative of that.
Wait, isn't this square root of the derivative of cos
It's a,
sine, and then
It's a
the
quotient rule.
derivative is sine is
it's
negative?
a quotient rule.
Yeah, I was 64.25.
It's a quotient rule. Like you take the
What do you mean
derivative.
chain rule?
Yeah,
No, be
chain-
product and chain rule.
Yeah. So you take the derivative of the inside and you bring it out.
Derivative of the outside and the inside fixed. Times the derivative of the outside and just go to the outside.
Yeah.
That catch courses again.
Where? Now, why do we draw a graph like this when we're talking about a box that's just moving left and right?
Because it's periodic, so it repeats itself.
Okay.
Why
So,
can only be 1 or minus 1?
What?
Why can only be 1 or minus 1? No, I don't.
Oh yeah, well, okay, this here is -1, no sorry, +1, this here is -1. Right? That's just how cosine, the function goes from plus -1.
All the time?
Yeah. If you, any value you plug into here, no matter what you put, the cosine of that will give you either plus or -1. Now, I want you to realize that if you take this thing and flip it like this, just in your head, it looks like this, and when the box is here or here, that corresponds to A or B. Okay, so as the box moves like this, or like this, it's going like that, and then with time, this just shows you that the box is just doing this. It's not really moving to the right. This just shows you that with time, the position of the box varies as it goes up and down. Okay? Now, because you have an A in front, the plus or -1 will be made smaller or bigger by the factor of A. If A is 5, this will go from plus to -5. Plus 5 to -5. You see what I mean?
What chapter is this from?
This is in the chapter of simple harmonic motion, like 13 or something. Huh? Huh? 15. Chapter 15. So, to get to your question about the initial phase angle, if I move the box to the right all the way and I let go, when it starts moving this way, it's going to be moving towards the left, or it's going to be moving from here towards here. Because it starts at the top here, and this is a cosine function, it starts at its maximum, +1, and just going down. Therefore, the function I have here perfectly matches a cosine wave. Although, if on the other hand, if I put the box here, and then let go, it will start moving this way. That would correspond to the box being here, and then moving towards the center. And so it would go like this, and like that. In this case, for this to match a cosine wave, I have to add a factor of pi to flip it by half a period. That way now, I'll be at this point and it will correctly match what a cosine wave is. So the way to find it is you just, let's say they tell you, okay, we have, at the beginning, I move the box to a point over here, which is at minus the amplitude, right? Because this is plus the amplitude is over here, this is minus the amplitude. So if I say, initially, my position at time t equals 0 is minus a, because it's here, or some other value like -2, it could be anything. You just put minus a is equal to a cosine of omega times 0, because it's 0 initial time, plus 5. And then since you're trying to solve for the phase angle, if you didn't know what it was, you just say a and a cancel, so I have -1, cos inverse of -1 is equal to 5. And that's how you can solve for the phase angle.
So the phase angle is 0 when we start from the equilibrium?
No, it's 0 when we start from the amplitude.
From the maximum amplitude. And when
On
we
the
start
right.
from whatever other point, that's when we have this phase.
Yes, exactly. Now, if you start from here and are moving that way, then you still are the amplitude, but on the opposite side, moving the other way, so then you have a phase angle. Now, the one time you have to use a calculator in radians, and when you're plugging in things into here, all of this has to be in radians, okay? Like, your calculation should be in radians when you're working with these equations. Because you have omega is in radians, and your phase angle is also in radians, you have to make sure you're calculating radians. Alright, more on this, next class.
Do you start new problems in each tutorial? Or you
Sort of, like I've already went over all of this stuff in